Welcome back, guys. We continue with section 14.6 about directional derivatives and gradient vectors. So if you remember, we almost stopped here last time, and we were talking about the gradient vector, which is obtained by the first partial derivatives of two variable function f, the first partial derivatives with respect to x and y, and you obtain what we call the gradient of fxy. Okay, and this gradient was used, for example, in this case, you could determine for f of x equals sine x plus exy. You could determine the first partial derivatives. So the derivative with respect to sine was equal to cosine x plus y exy. And with respect to y, you got the derivative, which is x exy. So at the point 0, 1, you could determine what is the gradient vector, which is, for example, at 0, 1 should be 2, 0. Then we use this gradient vector to find another way to write in a more simple manner the directional derivative with respect to a vector u. So we write the directional derivative with respect to u of fxy as the gradient vector multiplied by just by u. Okay? Remember, we always try to take u as a unit vector. Then we talked about functions of three variables. So we extended the problem and we wrote the definition of the directional derivative. And if u, for instance, had components a, b, c, then this is the limit definition of the directional derivative, which is just an extension to a third variable z and third component c of the same one we've seen with two variable functions. And we wrote it also using the gradient. If you recall, we defined the gradient for three variable functions, and we wrote the directional vector using the gradient. It's exactly the same, okay? And for instance, let's continue here. From example 5, we have if f of xy is equal to x sine yz. We solved this case, if you remember, at the end. We wanted to find the gradient of f and find the directional derivative at 1, 3, 0 in the direction of v equals 1, 2, minus 1. Okay? So first of all, the derivatives, if you differentiate with respect to x, you get just sine yz. If you differentiate with respect to y, you will have the z that goes outside, and you have xz cosine yz, because the derivative of sine is cosine. And if you differentiate with respect to z, you will get the y that goes outside, and you get xy cosine yz. Okay? So this is the gradient vector. Now, you need to find the directional derivative. You need to find a unit vector from v. So we divide. In fact, you may write u as v divided by its norm, by the normative. Okay. So basically, you will divide by the square root of 1 plus, so 1 squared plus 2 squared, which is 4, plus 1 minus 1 squared, which is, so basically you multiply by 1 over root of 6. So this is the vector. Okay. So it's 1 over root of 6. Multiplied by 1 to negative 1. Okay. Once this, all you need to find to determine the directional derivative with respect to u is to multiply the gradient by u. Okay, using a dot product, of course. Okay. So you multiply this vector by the other vector. So this is what we got here. We at 1, 3, 0, we determine the gradient, which is 0, 0, 3. Using the solution we found, or the result we found on the gradient, and we just multiplied now by u, which is as we detailed previously, and this is the directional derivative. We find that it's minus square root of 3 over 2 at 1, 3, 0. Okay, so that was the last example we solved last time. So today we continue from there, and we talk about maximizing the directional derivatives. So let's suppose that we have a function f of 2 or 3 variables, and we consider all possible directional derivatives of f at a given time. So this, in fact, these give the rates of change of f in all possible directions. And of course, we are looking for the one that possibly maximizes the directional derivatives. You may call it as the greatest ascent or the greatest descent if you're willing to minimize. So we can then ask the questions, in which of these directions does f change fastest, and what is the maximum rate of change? Okay, so if you're willing to maximize, you want to go higher in the fastest direction. If you are willing to minimize, you want to go deeper in the direction with the maximum rate of change, or the lowest rate of change, of course. So the answers, in fact, are provided by the following theorem. So if you suppose that f is a differentiable function of 2 or 3 variables, so a multivariate function in general, the maximal value of the directional derivative du times du f is in fact the absolute value of the gradient of f. Okay? And in fact, this happens when you have the same direction as the gradient factor. Okay? So if you're willing to look onto the greatest ascent or descent direction, well, you just have to follow the gradient. Okay? So this is pretty simple. And from a numerical point of view, many algorithms were based on this theorem. The conjugated gradient, the gradient ascent, the gradient descent, and all things like this. Okay, so let's take this example. For example, you see this a little bit complicated function, x, ey. We'd like to find the rate of change of f at the point p with coordinates 2, 0 in the direction from p to the point q, half 2. So basically, we have the vector pq here, okay? Which you can use still determine. So what is pq, guys? You're going to have half minus 2, which is minus 3 over 2. And the second component is 2 minus 3. So this is pq. We want to go in this. So we'd like to find the rate of change or the directional derivative following this vector. What do I need to do? I need, first of all, to compute the gradient. So the gradient of f here with respect to xy, you need to compute the first derivative with respect to x. It gives you ey. And the derivative with respect to y, it gives you x ey. Okay? It's pretty easy because you just have y as an exponent here. Now at the point 2, 0, you get e of 0 and 2e of 0. So you just want 2, and this is your gradient. So the directional derivative following pq, okay, would be given by the dot product of the gradient by the vector, in fact, pq divided by its norm. So this is what we're going to do here. First of all, we determine pq as we did in the previous slide, and we divide it by the norm of pq. Here, the norm of pq is going to be the square root of 1.5 squared, of course, plus 2 squared. Okay? So if you want to write it in more in fractional form, it's going to be 3 over 2 squared, so it's 9 over 4. Plus the 4 here is 16 over 4. So basically, you end up with root of 25 over 4, so it's 5 over 2. So this is the norm of PQ. And if you divide by the norm of PQ, which is 5 over 2, you're going to obtain this vector, which is a unit norm vector. So the rate of change of f in the direction P to Q is given by the dot product gradient by u. So you multiply just your gradient 1, 2 by your vector u, and you will have 1 times minus 3 over 5. So it's minus 3 over 5 plus 2 times 4 over 5. So you get minus 3 over 5 plus 8 over 5, which is just 5 over 5, which is 1. Okay? So in fact, according to the previous theorem, what does it say? It says that f increases the fastest in the direction given by the gradient vector at 2, 0. which is 1, 2. That maximum rate of change is given by the absolute value of that, by the norm of that gradient, which is the norm of the gradient here is going to be the square root of 1 squared plus 2 squared. Okay. So this is the rate of change, the greatest or the maximum change. So you get the root of 5. Okay. Got it, guys? Any question on this? Okay. So now let's talk about tangent planes to level surfaces. Okay. So first of all, let's suppose that S is a surface with equation given by fxyz equals k. So you see k here is supposed to be a constant. That is, it is a level surface of a function f of 3 variables. And let this point x0, y0, z0, or x0, y0, z0 to be a point on that surface S. So we let also see any curve that lies on the surface S and passes through the point P. So C is part of the surface and passes the point. Recall that the curve C is described by a continuous vector. For instance, you may call it RT with xt, yt, zt. Okay? Parameterized curve. So let T0 be the parameter value corresponding to P. Okay? So at which T, in fact, that curve goes through the point P. That is, R of T0, x0, y0, z0 is going to give you P. Okay? Since C lies on C, any point, in fact, with the following component, with the following coordinates xt, yt, zc, must satisfy the equation of S, that is f of x t, yt, zt equals k. So you must satisfy the surface level or level surface equation. Okay? So if x and y are differentiable functions of t and capital F is also differentiable, then we can use what we've seen in the previous section, 14.5, the chain rule, to differentiate both sides of equation 16 and obtain the following. It means that the derivative of f with respect to t needs to be equal to 0. Okay? But since, in fact, what you had here in front here of the dx over dt, dy over dt, and the df over dz is just the gradient of capital F, and the derivative fact of self of the RT is given by these components, x prime, y prime, z prime, then what you can say is that this gradient multiplied by the r prime of t equals 0. What does this mean, guys? If this dot product is equal to 0, what does it mean?
They are perpendicular to each other.
Thank you, Alfred. It means that, in fact, that gradient vector is orthogonal to the curve, right? Where? At the point, of course, of concern at the point. Got it? Okay? So, in particular, when t equals 0, when t equals 0, we have r of t0, which is x0, y0, z0. So, in fact, we have a scalar product or dot product that equals to 0, which means that the gradient, in fact, at the point x0, y0, z0 is perpendicular to the tangent vector r prime of t0. And this is the right way to see mathematically how it should be plotted. Okay, so gradient is perpendicular to the tangent. Got it, guys? Okay, so geometrically, this is what's going on. Gradient is going to be orthogonal to the tangent curve. Okay? If it is orthogonal to the tangent curve, it means that it is orthogonal to the level surface, of course, to which belongs the curve. Okay, guys? Now let's move on. So if the gradient now, of course, is not 0, it is therefore natural to define the tangent plane to level curve f of x, y, z equals k as dx0 y0 z0 as the plane that passes through P and has a normal vector, which is the gradient. You see, since we just said that the gradient is orthogonal to the level surface, then we can consider it a normal vector, which means this would help definitely. Don't forget that when we talked about planes, we said one way to write the equation of plane is just to take the normal vector. So you see now, to write the equation of our tangent plane, you just need to take the components. That's it. So the component of the gradient come as the constant for of x minus x0, y minus y0, z minus 0 in the tangent plane equation. Got it, guys? Okay. So it is very trivial mathematically to get this. So what do we say? So at the point P x0, y0, z0, the plane passes through P and has a normal vector. We can write the standard equation of the plane using the gradient vector. Okay? So I'm not able to move forward with my slides. Okay, now move forward. So moreover, if I go back, yeah, it goes back. So the normal line to S, what is a normal line to S at P? So it is perpendicular. Is the line passing through P and perpendicular to the tangent plane. So it's a line that goes through P, which is in fact tangent which is perpendicular to the tangent plane, which means it's a line that is carrying the gradient, as you've seen in the figure. Okay, so if you go back just in this figure, the line would go just like this. Okay, got it? So the direction of that normal line is therefore given by the gradient vector, and so it is symmetric. Its symmetric equations are given by this equation. You can easily find it as the canonical form or symmetric equations of the line could be written as x minus x0 divided by fx equals y minus y0 divided by fy equals z minus z0 divided by fz. Okay, we have a direction vector which is the gradient. Okay, so here I think we can skip this, and I would like to talk about the example. So we'd like to here, for example, to find the equations of the tangent plane and the normal line at the point -2, 1, -3 to this ellipsoid. Okay? First part of the methodology to follow to solve the problem is to do what? To find the gradient of f. So suppose here that you have f of x, y, z equals k. So basically here your f of x, y, z is x squared over 4 plus y squared over 1 plus z squared over 9. This is an ellipsoid form, of course. And if you differentiate, what do we have, guys? Tala Ali, what are the derivatives? Maybe Abdul Karim is still with us.
2x, x over 2.
X over 2, okay. df over dy.
2y.
2y. And the derivative with respect to z is
2z over 9.
2z over 9. Okay. So basically, we got the, what is this? I don't know what it is. Okay. So basically, we got the gradient factor. Okay. You see the components. So at that point, what are the values of the what is the gradient at that point? At -2, 1, 3. 1 minus 3. You're going to have -1, yeah, 2y, which is 2, and here we have 2 over 9z, so it's -6 over 9 or -2 over 3, right? Okay, it's -3 times 2 over 9, so it's -6 over 9, so it's -2 over 3. Okay, So once you got the gradient, so we said we have again the first derivative was x over 2. Second derivative of y is 2y, and the derivative with respect to z was 2z over 9. Okay, and we just found the gradient. So the gradient at minus 2, 1, 3, we just said it was equal to -1, 2, and minus 2 over 3. Okay. So what is the equation of the plane, guys? Tangent plane. What should how should I write it? This is a normal. The gradient is a normal to the tangent plane. So it's going to be -1 times x minus x0 plus 2 times y minus y0 minus 2 over 3 times z minus z0. It should be equal to 0. Got it, guys? Now you just need to plug in, instead of x0 and y0 and z0, you plug the corresponding values, which are -2, 1, and -3. Okay, so you end up with pi t tangent plane, which is minus x plus 2y minus 2 over 3z equals, now let's add up the constants. I have -1 times plus 2. So it's -2. Bring it to the side, you get -2. And have -2y0. So I have -2. So it becomes +2. And on the other side, I'll have -2 over 3 times +3. So it's -2, so it's +2. Okay? So basically, this is the equation. It's minus x plus 2y minus 2 over 3z equals +2. Okay? This is the tangent plane. Now I can let you do the normal line. Of course, normal line we gave you x minus x0 divided by -1, y minus y0 divided by 2, and z minus z0 divided by -2 over 3. Okay? These would be the symmetric equations of the normal line. Any question on that, guys? Okay, no questions. Everyone is following. So let's take a short break, if you wish. Or let us finish. Let's finish. Okay, so that was the solution we just worked out. Okay. Therefore, one can say that we have these gradient. This is the gradient. These are the answers we just found, and here is the equation we just solved. I think they got something which is how much? That's right, 18. It's definitely wrong, right? And they just multiplied. Okay, they multiplied. I think they multiplied by something by -3 or something. With this 18, we found a different form. Okay. So, and finally, this is the symmetric equation. Right. So let's move on. Now let's talk about the significance of the gradient vectors. We now summarize the ways in which the gradient vector is significant. We first consider a function f of 3 and point with coordinates x0, y0, z0 is domain. On the one hand, we know from theorem 15 that the gradient in fact gives the direction of the fastest increase. On the other hand, we know that the gradient of x0, y0, z0 is orthogonal to the level surface, which is tangent to the level surface S of f through the P. Okay? So these two properties, in fact, are quite comparable intuitively, because as we move away from P on the level surface F, the value of f does not change at all. So it seems reasonable that we move in the perpendicular direction, and we get the maximum increase. In like manner, we consider a function f of two variables, and we can work with a point P with coordinates y0, z0, and we can say that that gradient f x0, y0 gives the direction of the fastest increase, in fact, of f. And the same thing apply, in fact, to multi-dimensional cases. Okay, guys? So this is for a two-dimensional case. This is the level curve, and this is the gradient, which points in the fastest increase, and which is orthogonal, as you can see, to the tangent line. And my slides are stuck again. So I think it's okay. So we can move on. So this is just to give you more ideas how if we can move from deepest ascent following the gradient. This is what happens in fact in this problem. So here we have a topological map of a hill, and f of xy represent the height above sea level at the point xy. Then a curve of steeper ascent can be drawn by making it perpendicular to all of the contour lines. And you can get the steepest ascent curve. As you can see that all they share in common and that it is perpendicular to all the level curves. This is another case where you have, this is like a magnetic field. And each gradient here is plotted starting at the point. And for the function, for example, x squared minus square, this is superimposed on the contour map of f. So as expected, the gradient vector points uphill, and the perpendicular to the level curves. Okay. So this is the last slide. I'll stop sharing this, and we will move on now to a more practical part. Let's solve on the blackboard. Okay. So I'll give you examples to solve, and we'll detail these examples. Hopefully, everyone will participate this time. So I'll take the textbook section 14.6 as usual, and move on to the exercise part, where we have a set of interesting problems to solve. So, for instance, I can start with this exercise. So this one is exercise number 7, page 957. Okay, and here we have f of xy, which is equal to x over y. Point is 2, 1, and I consider u to be equal to two over 5i, 3 over 5i, plus 4 over 5j. Okay, got it? So what do we ask for is to find the gradient of f. Second question, we'd like to find the gradient of f at that point, at 2, 1. And finally, find, of course, the rate of change in the direction of the vector. We'd like to find the directional derivative at that point. Okay? Go ahead, guys. I'll call on your names, okay? I'll stop recording here just to avoid having your names with the video.